Hello, and welcome to MiniLecture 24 on the stability of equilibria. All right, so this concludes our 3 lectures on differential equations. In the first lecture, we talked about what a differential equation was, how to get that differential equation from a flow diagram, and how to solve that differential equation using guessing and checking. In the next lecture, we talked about the equilibria of differential equations. Equilibria describe the possible, emphasis on possible here, possible long-term outcomes of a differential equation. And in this lecture, we are going to talk about the stability of those equilibria. So the equilibria are the possible outcomes, and stability will tell us which one of those outcomes actually occurs. All right, so let's start with some review. 2 lectures ago, we talked about what differential equations were and how to derive initial value problems from flow diagrams. Let's do this again for the case of logistic population growth. We start by taking the derivative of our state variable. In this case, that's n. It's the thing inside the bubble. We have bn times 1 minus n over k minus dn. So flow in minus flow out. And we have our initial condition, n0 is equal to 10 in this case. All right, then we want to find the equilibria of the system. We do that by setting the differential equation equal to 0. It is no longer a function of n then, or of time, so we use hats instead of n's. N hat divided by k minus dn hat. So when we go to solve for a differential equation, this is a good time to remember that we want to check the trivial solution. What is the trivial solution in this case? Well, the trivial solution is that n hat is equal to 0. This is the boring case of extinction, where if this term has an n hat in it and this term has an n hat, if n hat is equal to 0, this term will go away and this term will go away. So we'll have 0 equals 0 minus 0, which is indeed the case. And so we have a trivial solution in this case of extinction. All right, but we don't just have extinction. In addition, we can multiply both sides of this equation by 1 over n hat, in which case we'll get a 0. This 1 over n hat will cancel with that and cancel with that. So we have 0 is equal to b times 1 minus n hat over k minus d. Now remember, when we solve for equilibria, we're trying to solve for this n hat here. So how do we get that n hat by itself? Well, let's move d to the other side of equation and divide by b. So we have d divided by b is equal to 1 minus n hat over k, which implies that n hat over k is equal to 1 minus d over b, or that n hat is equal to k times 1 minus b over, 1 minus d over b. All right, so there's another way to write this, which simply happens by multiplying this by b. So we have b over b, which is another way of writing 1, and combining these into a common denominator. So we have k is equal to b minus d over b. So n hat is equal to that. That is our second equilibrium here. So we now have found our 2 equilibria of this system, which is good. All right, what do these 2 equilibrium tell us about the possible long-term outcomes? This is extinction, and this is called carrying capacity. So this is if a population keeps on growing until competition keeps it from capacity. There you go. Carrying capacity. All right, but we have 2 possible outcomes. Which outcome actually happens? Well, in order to figure this out, we have to look at the stability of the system. All right, in order to find the stability, you're going to use something called a phase plane. So if we have the differential equation, df dt is equal to some function f of, or in this case, dn dt is some function of n, then we want to look at how this function n looks. So we're going to plot f of n over here. So we have f of n as a function of n. So we're plotting f of n as a function of n. So we usually think of n as our dependent variable, but in a phase plane, the n is going to be our independent variable, and the right-hand side of our differential equation is going to be our dependent variable. So f of n here is on the y-axis, and n is on the x-axis. If we have this, then we have this curve that I've drawn here. Now the equilibria are by definition when this dependent variable, this new dependent variable, equals to 0. So there are two equilibria here. There's the one at 0 and the one at carrying capacity. All right. In order to figure out the stability of this system, I want you to think about the slope of the tangent line to this curve at these two equilibria. So you know how to do that. That's the derivative of the dependent variable, in our case f, with respect to the independent variable n, df dn. And I'm going to claim that if this is less than 0, then the system is stable. All right, and that means that we go to this equilibrium. So if we take the derivative of a function and we plug in the equilibrium, and that is less than 0, then we will end up going to this equilibrium. To think about this, we can think about what happens if we are bigger than this equilibrium. So what if we start out and we're above carrying capacity? We start out here. Then this derivative tells us that the population size is shrinking. The change in the population size with time, dn dt, is negative, which means that we are going to end up getting a smaller population size. We're going to move to the left, so the population size is going to get smaller. So we're going to get closer to that equilibrium. If we start out and we're much less than that equilibrium, say I'm there, I look at my change in my population size. I'm here, so I have dn dt is positive. That means that my population size gets bigger, and I'm going to move this way. So if I'm smaller than the equilibrium, I'm going to move toward the equilibrium. If I'm larger than the equilibrium, I'm going to move back toward the equilibrium. So this guy over here, this equilibrium, is something that we call stable, and that means that for these parameters, I'm going to approach this carrying capacity equilibrium. Alternatively, if we go and look at this equilibrium over here, and if I start above the equilibrium, we can't start below it because it's 0. If I start above it, I go and I look at my change in population size, and it's positive. That means that my population size is growing. So my population size is going to move to the right, and I'm going to end up moving away from the equilibrium, which means that this is unstable. All right, so we can all get this from the slope of this tangent line, because if that slope is positive, then you're going to move away from the equilibrium. If that slope is negative, you're going to move toward the equilibrium, and you're going to end up at the equilibrium. So we want to know the slope of the tangent line of f of n with a function of n at a particular equilibrium. All right, instead, formally, we want this derivative, and we want to know when that derivative is less than 0. All right, so in our case, we have dn dt is equal to bn 1 minus n over k minus dn. All right, so this is our f, and we're taking the derivative of this function f. Oh, sorry, I should use capital F. Taking the derivative of this capital function f here with respect to n. So let's do that derivative. All right, you guys know how to do this. We can split this derivative up into two terms depending on the sum. The b minus d is just a constant, dn dt is 1. Then we have the second term, b over k is a constant. We use the power rule, and we have 2b over k times n. All right, now this gives us this curve here. So we just found, f here is this curve. We just found the slope of the tangent line, but we have to evaluate that tangent line at a particular spot. So this is the slope of the tangent. This is our phase plane curve. But now we want to evaluate the slope of this tangent line either at this equilibrium here or at this equilibrium here. All right, so let's do it at the first equilibrium. The first equilibrium was n hat equals 0. So I'm going to take my slope of my tangent line, my b minus d, over 2b over k times n, and my n is equal to 0. All right, if I do that, this term drops out, and I simply get b minus d. Plugging in these parameter values, I end up with 0.2 minus 0.01, which gives me 0.19. All right, we want to know if this is greater than or less than 0. This is greater than 0, so this is unstable. So this equilibrium here at n hat equals 0 is unstable, and that's what we found in our diagram. All right, the second thing we can look at is we can look at equilibrium 2. So I'm going to plug in n hat is equal to k times b minus d over b. All right, so if we plug this in, we have our slope of our tangent line, b minus d, minus 2 over k times 2b minus d over b. Oh my gosh, let's do this again. Okay, times k b minus d over b. There we go. All right, this k here cancels with that k there. That b cancels with this b there. So we end up with b minus d minus 2b minus minus, so plus 2d, which is equal to d minus b. All right, plugging in these parameters, which are the same as we had up here, we end up with 0.01 minus 0.2, which is equal to minus 0.19, which is less than 0, so this is stable. All right, so what does it mean to be stable? It means that this slope is negative. We end up approaching this equilibrium. So we have these two possible outcomes of our system, and we end up going toward this outcome. All right, so once again, we found our two equilibria. We figure out that the one at extinction is unstable, so you don't approach extinction. Instead, you approach carrying capacity. Note that in order to calculate the sign of this, we had to plug in some parameters. So we had to plug in that b and that d. What stability we get depends on the parameters we plug in. So this was our original curve that I just showed you. And in this original curve, this had a tangent line of positive. This had a tangent line. Come on. This had a negative tangent line. And so this ended up being our stable equilibrium. In this one, I've increased the death rate by a whole bunch. So I went from a very small death rate to a very high death rate. If the death rate is really, really high, what happens is the population ends up going extinct. And so the slope of the tangent line at extinction ends up being negative. So we end up approaching the extinction equilibrium. So the stability of the equilibrium can depend on the parameters. For example, in this case, birth was greater than death, so you end up going to carrying capacity. In this orange case, death was greater than birth, and so you end up going to extinction. All right, with that, I'm going to leave you with a practice problem about the Lie effect model.